So we've been learning a lot about plant communities today, and native plants are certainly the foundation of a thriving ecosystem. But of course, what supports that is soil. So that's what we're going to be learning today. And Dan Schwartz joins us. He holds a bachelor's and a master's degree in environmental science from the University of Maryland and Virginia Tech. Since 2003, Dan has worked as a soil scientist for the Northern Virginia Soil and Water Conservation District. His first years with the district were spent outdoors doing field work to update the Fairfax County soils map. Since then, his work responsibilities broadened to include outreach and education, technical consultation to county agencies, soil and stormwater research, erosion and drainage assistance to Fairfax County homeowners, and implementation to the district's residential cost share programs. And it is with great pleasure that I will pass this presentation on to Dan. Dan, thank you so much for being with us and sharing your wealth of knowledge about soils.
Thank you very much, Ashley. It's a pleasure to be here. Pleasure to be talking to so many people who willingly give up their Saturday to hear about soil. That's always a treat for me. So let's get into it, because I know we don't have too much time. Let's see if I get my slides advancing. Hold on one second. There we go. So, you know, I don't know which breakout sessions you were in before this, but I was watching Dr. Cullens, and she had a great overlap with what I'm about to speak about as well too. So if you're in her session, you're going to hear some information repeated. But what I really want to stress today is that soil is not just this physical material. It's an ecosystem. There's a whole world below our feet, which isn't all that well known about because it's invisible. And it's very, very close to us. It's literally just a few millimeters below the soles of our shoes, but we can't see it because it's just buried underground. So to us, what grows on top is obvious, and what grows on top are all the plants that we're trying to grow, the natives. And we can see those, of course, but really half of that ecosystem exists under the ground as the soil roots. And around those soil roots, there's a whole other ecosystem of critters, both big and small, that are very, very important and essential for a healthy plant growth. So what I want to talk about today is that ecology below ground. It's what lives below that really makes everything above possible. So if you want that nice assemblage of native plants, of flowering plants, of pollinator-friendly plants up in your yard or on your school, at your church, wherever it may be, you need this healthy soil ecosystem below to make it all possible. And this whole ecosystem consists of billions and billions and billions of organisms, most of which are so small that they're not visible to us. Let's step back a little bit, though, and talk about what soil actually is. So conceptually, this isn't so much of a scientific concept, but more just something to kind of wrap your head around. Conceptually, I like to think of soil as being the skin of the earth. So right there at the earth's surface, where the atmosphere and the physical matter of soil, of the world interact, that's really where we find soil, just that thin crust right over the surface of the solid material. We can kind of break down the world into three general spheres of matter. There's the hydrosphere, which is all of our water from the biggest ocean to the Potomac River, to the Chesapeake Bay, to the small streams that feed into it, to the little microscopic particles of water vapor up in the atmosphere. All that combined together is the hydrosphere. There's the lithosphere, which is our bedrock, basically the solid rock that makes up a good portion of the earth. And if you dig down deep enough, no matter where you are, you will eventually hit solid rock. And then there's the atmosphere, which is self-explanatory, the air above us, where we have all three of those spheres mixing and combining together right at the surface of the world. That's where we get our soil. And this concept is important because when we think of soil, we usually think of it as being a solid. And that's not wrong, but it's incomplete. So it's probably comes as a bit of a surprise that healthy soil, and I do have to emphasize the word healthy, because certainly in urban, suburban areas like Prince William County, like the rest of Northern Virginia, a lot of our soil is not, unfortunately, healthy. But if you do have healthy soil in your yard, what it consists of is only about 50% by volume solid material. And the other 50% of the soil, the other half, is usually divided pretty evenly between a 1/4 air and 1/4 water. So 1/4 of the volume of the soil is actually the soil gas, soil atmosphere. 1/4 of the volume of the soil is water. This changes from day to day. If we have a really rainy day, soil might be 50% water, 50% solid. If we've been going through a really dry patch in the middle of July, we might have quite a bit less water than 25% in the soil at any one time. But the yearly average, this is what a healthy soil looks like. I'm going to talk a lot about the organic portion of soil. And despite its importance, it's not all that big, at least in terms of its volume. About 5% of the soil is organic material. The other soil solids are minerals, and that's about 45% of the volume of the soil. So that 5%, while small, is still incredibly important when it comes to soil health and the health of the plants that are growing within that soil. So even though soil solids are perhaps a little bit less numerous than we might have thought, and they're not quite as dominant, only 50% of the soil is solid, they're still very important for us, and they often are the way we talk about soil. When we're talking about what our soil is or how it differs from soil in other parts of the county or other parts of Northern Virginia or other parts of the world, we're really talking about differences in soil solids. So what are those soil solids? Well, again, we can break them down into two fractions. There's the mineral fraction, 45% of the volume of the soil, and the organic fraction. Your mineral fraction consists of sand, silt, and clay. And the differences between sand, silt, and clay are purely differences in size. So sand is the largest of the mineral particles, silt is the middle child, and clay is the smallest. They all seem small by our standards, by our human scale, but there is a tremendous amount of size difference between a particle of sand, a particle of silt, and a particle of clay. You don't have to memorize these numbers by any means, but it gives you an idea of the dispersion that we're talking about. So the US Department of Agriculture defines any mineral particle in the soil with a diameter between 2 and 0.05 millimeters as being a particle of sand. Silt is anything between 0.05 and 0.002 millimeters in diameter, and then clay is any mineral particle less than 0.002 millimeters. That's the same as 2 microns. Which is 2 millionths of a meter, so very small. Think of that 3.25 foot or so long meter. You take that meter stick and slice it into a million equal parts and put 2 of those millions together, 2 of those slices together. That's the diameter of the largest particle of clay. And they get a lot smaller than that as well, too. So I was listening to a master gardener present several years ago, and the analogy she gave is if you've ever gone to, got to get the name right, the Washington Commanders game, the sand is sort of akin to the stadium itself. Silt would be like the size of your car compared to the stadium, and a particle of clay would be like the parking ticket or the parking pass on your windshield compared to the car, compared to the stadium. So when we blow it up into those sort of terms, it kind of gives you an idea of how different in size these things really are, even though they all seem small to us. That's the mineral fraction. Your organic fraction consists of your living and your dead materials. Anything alive in the soil, we actually consider to be part of the soil. That's beetles, your burrowing earthworms, the plant roots themselves, or in particular, these little guys, the small insects, arthropods, the fungi, or the bacteria. So for a teaspoon of healthy topsoil, it's estimated there's anywhere from about 100 million to 1 billion bacteria residing within that teaspoon. For fungi, it's a little bit different. There's a lot of fungi in soil too, and especially a lot of fungi in forest soils. They tend to like soils that have a lot of woody debris that drops to the floor. Fungi are usually not single-celled, though. They usually exist as these really tiny, microscopic little root hairs. They look like tiny little white twine working their way through the soil. Sometimes a bunch of them combine together and they do get big enough that you can see it, but for the most part, they're microscopic. We could extract all these little fungal root hairs, which are called hyphae. We could extract all this hyphae and lay each one end to end to end. For every teaspoon of healthy topsoil, we'd find that the length of that soil fungal hyphae ranges from about 40 yards per teaspoon to 40 miles per teaspoon. And again, those higher numbers, the miles and miles per teaspoon, are generally found in our forest soils where there's a lot of woody debris decomposing on the forest floor. So the bottom line is there's a ton of stuff, literally tons of stuff, billions and billions and billions of these little microbes and larger organisms living in our soil. And because most of them are microscopic, they're mostly invisible to us, but they are there. And then there's the dead material as well, too. The dead material, the decomposing organic material, is just as important as the living because this is the food source for that living organic material. The living bacteria, fungi, arthropods, worms, They're munching down on this decaying organic material, our leaves, our twigs, animal manures, and they're turning that into themselves. They're basically creating energy for themselves so that they can grow and reproduce. Moving back real quickly to the soil solids, you might have heard of a soil physical characteristic called soil texture. Basically, if you say, oh, I've got red Virginia clay in my yard, you're making a comment on the soil texture. The soil texture is the percentage of sand, silt, and clay in a soil. And it's very important because it has a large effect on the ability of that soil to retain water, retain nutrients, and its ability to infiltrate material. Infiltrate means to pass water or oxygen from the surface down into the soil and into the pores. Basically, infiltration is the measurement of how porous the soil is. And texture is very important because if you have a bad texture, you can have sort of a difficult soil to manage. So these are some pretty reductive graphs, but I think they're useful. These graphs are showing just basically the relationship of water holding capacity, nutrient holding capacity of a soil, and the infiltration capacity of soil. Again, the ability of soil to soak up water and oxygen from the surface. And comparing it to its texture. So let's say on these x-axes, we have this hypothetical soil where we can change the texture at will. We can go from a very sandy soil over here, 100% sand, and then we start subtracting sand and adding clay. So we go from really sandy to 100% clay over here. What happens to the water capacity as we add or subtract sand? Well, let's say we start with 0% sand, pure clay, and we start adding more and more and more sand until we basically get to beach sand over here. As we add more and more sand to our soil texture and subtract silt and clay, what we'll find is the sandier soils have less water holding capacity. As we take our soil texture and add more and more clay, the clayier soils have greater water holding capacity. Probably not too much surprise to you. Nutrient holding capacity, same thing holds. Add more sand, the sandier the soil gets, the less the ability of that sandy soil to hold nutrients, to bond nutrients inside the soil. As we add more clay, the more clay you have, the more ability that soil has to hold nutrients. But this pattern switches when we get to infiltration capacity, the ability of air, oxygen, and water to soak down into the soil in the first place. As the soil gets sandier, the infiltration capacity of that soil increases. As we get clayer, we start gumming up the works with all that sticky clay. The more clay you have, the less infiltration capacity you have. The slower water and oxygen passes down from the surface into the soil and to the plant roots. And this is a shame because we want all three. We want good water holding capacity, good nutrient holding capacity, good infiltration capacity. But unfortunately, if we have too much sand or too much clay, we can at most get 2 out of those 3, but not all 3 of them. And the other unfortunate thing is texture really can't be practically changed. Sure, you could theoretically pay for 30 dump truck loads of sand to be mixed into your clay soil, but really, I wouldn't recommend it. So you're pretty much stuck with the texture you have. Now, going back to the soil solids and our organic fraction. The reason I sort of mentioned texture before is that the organic fraction actually can sort of sand off the rough edges of having a bad texture in your soil. So the organic fraction, just like the soil texture, has a large effect on water retention, on nutrient retention of soil, the infiltration capacity of your soil, plus the organic fraction also is sort of the controlling factor in the ability of your soil to cycle nutrients. And the real good news is, unlike texture, the organic fraction of your soil can be changed through management and changed fairly quickly. So you can't really change soil texture, but you can change the organic percentage of your soil. And this will help you to maybe not fully eliminate, but certainly greatly reduce the effects of bad texture. So what does the soil organic matter do? Well, it depends on the type. The dead organic matter, so all the leaves that fall off our trees during the autumn, the animal manures that get deposited on the soil, the dead animal carcasses themselves, the twigs and branches, or even something as simple as the blades of grass that you cut off your lawn and leave in place. That is the base of the soil food web, that decomposing organic matter that lands on the soil surface and eventually breaks down into soil humus is the base of the soil food web. So here's a very simplified view of our soil food web. It's much more complicated than this, but this kind of gives you the broad strokes of it. And down here at the bottom, you see we've got our organic matter. So all that dead decomposing organic matter coming from generally the plants feeds organic carbon and energy into the food web below ground. And then there's the living organic matter, and they are the processors of the dead organics. So within this dead organic matter is all the important nutrients that we have in need for good plant growth: nitrogen, phosphorus, potassium, iron, zinc. But it needs to be processed first. It basically needs to be decomposed in order for those nutrients to be released into a usable form that the plants can have access to. And sort of two big trophic levels of the soil food web that are important in this processing are the decomposers, which is, this is reductive, but basically it's our bacteria and our fungi. They are the ones that basically take that organic matter and decompose it into soil humus. And then we have our shredders, which are kind of actually, they come often before the decomposers. The shredders are your larger organisms like your, burrowing beetles and other insects that live in the soil, as well as the earthworms themselves, that take larger pieces of organic matter, shred it into smaller pieces. And the smaller they shred it, the easier it is for the decomposers to then come in and break it down. It basically gives them more surface area to work with. So that's not all they do, the shredders, of course, they're doing other stuff, but that's one of the primary, most important roles that they have within the soil food web, shredding down that bigger organic matter to make it into sizable chunks that decomposers can then access. The living organic matter also collects nutrients. So this is a screenshot of a small pine seedling. What we see here, what I've kind of highlighted in those dashed lines, that's pretty much the extent of that pine seedling's roots. So what are all these other roots that are there? Those are the mycorrhizae. And mycorrhizae are basically special fungi that live in the soil that actually invade and infect the roots, but in a good way. It's a good infection, because what they do is they kind of stick their ends into the plant roots, and then they extend their own very fine fungal roots out into the soil. And this ends up greatly extending the reach of that plant roots. The mycorrhizae collect nutrients and collect water from the soil, and they send it into the plant. What does the plant do in return? It sends carbohydrates, food basically, the stuff that it makes through photosynthesis, down into its roots to feed those mycorrhizae. So the mycorrhizae get fed while also providing water and nutrients to the plant, which is obviously a great mutualistic relationship. And the organic matter, the living stuff in soil, also creates what we call soil structure, meaning how the soil clumps together. And it seems like something as simple as that wouldn't be so important, but a soil with good structure, meaning well aggregated, clumps together nicely. Structure is really the controlling factor for the infiltration of soil. A well-structured soil is a loose, light soil with lots of pores that allows a lot of water and oxygen to quickly pass from the surface down into the soil and down to the roots where the plants can then have access to it. So good structure usually means a soil with good porosity, good infiltration. And the living organic matter is very important at creating this, details of which we'll get into in just a bit. So, going back to texture, when we talk about, oh, we've got this clay soil, I've got this sandy soil, what's to do? Well, the nice thing is, if you add a lot of organic matter to your soil, you can sort of decouple the negative effects of bad texture from the nutrient holding capacity. So even if you have that really, really sandy soil that just does not do a good job naturally of holding on to nutrients, if you're adding organic matter, you're firing up the soil food web. And as that organic matter is being decomposed by the fungi and the bacteria, they are creating soil humus, and in the process, they're also releasing a lot of nutrients that can be dissolved in the soil water and then taken up by plant roots when they're sucking up water out of the soil. So if you have bad texture, the trick to your soil is not to try and change the texture, it's to add organic matter so that you can get a good nutrient cycle going thanks to that organic matter and despite your potentially bad texture. So you can sort of take that negative effect of texture on the nutrient holding capacity, take it off the books, because now you've got your soil food web functioning very nicely thanks to additions of good organic matter, organic carbon. So soil structure, we started talking about that 2 slides ago. It's how the soil solids are clumped or arranged together. So soils naturally will clump into little aggregates that we call PEDs, P-E-D-S. If you go to a land-grant university like Virginia Tech or Virginia State or the University of Maryland, you'll see that the professors of soil science, their official term is pedologists, those who study PEDs. So we kind of think of PEDs as almost like the building block of soil, certainly the visible building block of soil. They're kind of like the smallest little bit of soil you can see, the little clumps that come up and you can see in the palm of your hand when you're digging through your own soil. And again, it doesn't seem like this should be that important, but it really, really is, because when you have a well-structured soil, which means you have PEDs that clump together fairly tightly and are water insoluble, meaning these PEDs will hold up even during heavy, heavy rainstorms. You don't want PEDs that hold together fairly well, but then dissolve the first time the soil gets saturated, because those dissolved PEDs will break apart and then basically clog up all the pores that you've got in your soil. You want PEDs that are pretty tightly held together and are insoluble to water, will not dissolve. And the reason that you want these good PEDs is not so much the PEDs themselves, but what occurs between the PEDs. So when soil clumps together, what separates each PED from its neighboring PEDs are pores or channels, open spaces that both air and water can use to pass through the soil, from the surface into the soil. So those pores between the PEDs are what we call macropores, meaning fairly large pores. They're sort of like the highways of the soil. They allow material to pass fairly quickly. Within the pores are micropores, within the PEDs are micropores, very small pores. And these are kind of like the wicking pores. You know, if you take a dry paper towel and you dip the tip of it into a bowl of water, you'll see that water start soaking up, moving up the paper towel via capillary action. These are sort of like the little tiny capillary pores which can hold water for a long, long time. So the macropores are really the more important ones for getting water down into the soil, down into the roots, and where water can flow in dry periods, oxygen will flow as well too. And that's very important because our roots need oxygen and water. So going back to one of the first slides we show, why is soil 50% solid, 25% air, 25% water? It's those pores which good soil structure creates that allows 25% of the volume of soil to be occupied by water and 25% of the volume of the soil to be occupied by air. Where do those things reside? They reside within the open pore spaces, especially the macropores between your PEDs. And organic matter is essential to the formation of good soil structure, because as organic matter decomposes into soil humus is one of those natural glues which causes PEDs to adhere together, but it's also a pretty non-soluble material. So it kind of coats the PEDs in a material that will prevent them from dissolving when the soil is really wet. And the ultimate result of good soil structure is a nice, light, loose soil, kind of crumb structure, or good soil tilth is something you might hear people say about it, meaning just sort of easy to work. It's loose, it's light, it's not dense and compact feeling. And on this nice, light, loose, well-structured soil, when you get the next rainstorm, almost all of that water is going to soak down through those big macropores between the PEDs. Fortunately, in an urban area like we have around here, a lot of our soil is compacted because it's been run over by machinery, it's been constructed upon. This tends to pack down the soil, and we get this much denser soil structure as a result. And this isn't an impermeable material, but when water falls on this dense, compact urban soil, some of the water goes through, but generally much less than would be soaked up by a nice, loose, well-structured soil. And this means there's more water on the surface, which can lead to ponding and puddling, or if you have a little bit of a slope, stormwater runoff. Again, it's really the organic matter that is essential to creating this structure, especially the bacteria and the fungi. They're the ones who are taking that raw organic matter and really powering its decomposition and turning it eventually into soil humus. Humus is actually a very resistant material. Humus is sort of like the hard to decompose stuff that's left after all the easy to decompose stuff has been broken down and taken up by the bacteria and the fungi. Humus can stay in soil for 50, 100, 150 years in many cases. And it's one of those natural glues that causes soil to first start clumping, which creates that soil structure. It's also very loose and light. It's a low density material, so it loosens up the soil as more humus is added to it. But of course, if all we had were natural glues, the soil would just be one big block. We also need our burrowing critters to create those pores, those channels that eventually become the macropores that separate one bed from another. Sort of the prototypical burrower in our soil is the earthworm. They're basically just tunneling all the time. And this is certainly, earthworms are not the only ones who do this role, but it's one that we're probably most familiar with. Another creature that's very important at creating burrows is the plants themselves. The roots are constantly spreading out and dying back. Each time a root dies, that old root channel becomes a great macropore as well. So you need both the clumpers, which are sort of the bacteria and the fungi, which create the humus, which is one of the primary natural glues that creates water insoluble beds. And then you need the burrowers to create the pore spaces between those beds. And luckily in a healthy soil, we have a lot of both. So let's go back to our effects of texture. Well, we just talked about soil structure and how it greatly impacts infiltration capacity. So if you have a really clayey soil, it's really dense and tight and hard for water to pass through. Well, the answer to that is get a lot of organic matter into your soil to feed those critters and create a lot of soil humus, which will loosen up the soil, cause it to clump into these nice beds, allow macropores to form and make that dense clay much looser, lighter, and more permeable. And then lastly, let's look at the water holding capacity of our soils. So the total amount of water that's held in a soil is actually not all that important. What's important is what's available to the plants. And the amount of plant available water is the difference between the volume of water held at field capacity minus the volume of water held at the wilting point. Field capacity is basically how much water is held in a soil about a day or two after a heavy, saturating, soaking rain. A day or two after the rain stops, some of the macropores have opened up and filled with oxygen again because some of that water is drained out via the force of gravity. But most of the smaller pores and even the medium-sized ones are still full of water. So this is basically the maximum amount of water that soil can hold against the pull of gravity. So the water that's more attracted by gravity or more pulled down by gravity is left, but everything else is still in there. The wilting point, on the other hand, is pretty self-explanatory. That's the level of water within a soil below which the plants start to wilt. And what you'll notice is, as we change our soil textures, we go from a really sandy, gritty soil and add some more fine material, so we get into a loam, which is kind of a mix of sand, silt, and clay, and then continue to add fine materials until we get to a clay. So very, very clay, very sticky, very, very little sand. The total field capacity will increase. That increase begins to level out as we move from the loams to the clays, but it's still going up. So clays actually hold the aggregate most amount of water. The issue is they hold that water very greedily. They don't share it very well. They're selfish. So water basically forms these films around the surfaces of clays, sands, and silts, and clays hold that film of water very, very, very tightly. So they hold a lot of water, but they hold it very tightly, so not a lot of it is available to the plants. So when you hit the wilting point in a clay soil, there's still a lot of water in the soil. It's just so firmly bonded to the clay particles that the plant roots don't have the energy to suction it off. In sands, you have very, very little water. Almost all of it is available to the plants, but they're just so little to begin with that your plant available water is not very great. The loams are the best texture in terms of available water because they hold a lot, but they hold it fairly loosely. So the distance between these two bars is a measurement of the plant available water. And you can see that the bars are the furthest apart when we have loams. But again, texture isn't something you can really change. You're pretty much stuck with what you have. So what do you do if you have a bad texture? A sand texture that doesn't hold water, or a clay texture that holds a lot but holds it too selfishly? You add organic matter, because organic matter has the benefits of clay without the negatives. If you add humus to soil, it greatly increases the field capacity because, like clay, humus can hold lots and lots and lots of water. However, unlike clay, it holds it very freely. It doesn't hold it very tightly. So almost all the water that bonds to the surface of humus is available to the plants. They have the energy to suck it up. So adding humus slightly increases the wilting point, but greatly increases the field capacity. And you can see no matter what texture you start with, the distance between the two bars, field capacity and the wilting point, grow greater, which means the plant available water with humus additions is greater. So again, we go back to texture. And the last negative effect of texture, some textures are not so great at water holding capacity or allowing the plant to have a lot of available water. The way you remediate that, as with all others, is by adding organic matter. It's delved very deeply into what a soil will look like. Up on the surface, well, I should back up just a second. I should say all soils are kind of like layer cakes. They come in layers called horizons. Each of these individual layers is called the soil horizon. The O-horizon, which often is a layer that most people don't think of as actually being part of the soil, but as soil scientists, we do consider a part of the soil, is this loose organic litter on the surface. So think of O as standing for organic. So it's actually the loose layer above the surface, which again, we usually think of the soil beginning below the surface, but as soil scientists, we do classify this O-horizon as part of the soil. So this isn't necessarily the brand new fresh leaves that you see falling on the forest floor, but if you take off that layer of fresh leaves, underneath it, you'll see another usually darker, usually a little bit moister layer of leaves that are beginning to break up into little particles. That's the O-horizon. So it's sort of the just beginning to decompose organic matter that litters the floor of the forest or any other soil for that matter. Where most of us think of the soil beginning is down horizon. This is our first subsurface layer. It's very rich in organic material. This is basically what we would call the topsoil. And this is the biological powerhouse of the soil. So all those billions of bacteria, those yards to miles of fungal root hairs, all those little roundworms, earthworms, the fine plant roots themselves, most of them are up in the A horizon. That's not to say that there's no organics below this. There certainly are, but it's much more concentrated in the A horizon because it's rich in organic matter. So obviously, organic matter is mostly coming from the surface and from the plant roots themselves. As the material from the O horizon starts to decompose, it's mixed into the A horizon, and this is where we get a really high percentage of soil humus. And in fact, the topsoil is stained this dark black to dark brown color because there's so much soil humus in it. It's not necessarily the color of sand, silt, and clay is usually kind of a pale gray, but it's the staining of humus that causes the A horizon to be this nice dark color. And oddly enough, even though this is probably, at least from soil health and soil fertility, and certainly from the soil ecosystem, from the soil food web, this is the most important layer. It's usually pretty thin in Virginia soils, just naturally. Even in a healthy forest soil, you'd be lucky to find 2 to 4 inches of A horizon. So even though there's a lot going on here, it's not a very big layer. Below the A horizon, we can sometimes, not always, but sometimes find an E horizon. I think of the E as standing for exit. It's a leached, pale, kind of washed out colored layer. And the reason for the E horizon existing is that in the A horizon, we're decomposing all this organic matter. One of the byproducts are humic acids and other organic acids. And as these acids wash down with rainfall deeper into the soil, they kind of not erode away, but they sort of leach away the materials in the E horizon. So the E horizon is kind of like the acid washed layer of the soil. The natural acids kind of leach materials out of this layer and deposit those materials deeper in the soil. The B horizon is one of those areas where these materials deposit. When you're talking about red Virginia clay, which I'm sure a lot of you have, what you're really talking about is the B horizon. The B horizon is where the clay deposits. And again, that's not to say you won't have any clay in your A or your E, you certainly will, but the B horizon is where it's the most notable and in the highest concentrations. And remember, clay is one of those really tiny particles. So a lot of it is actually forming up in the A and the E horizon, but over time, as that soil weathers, as rainwater and snow melt passes through the soil pores, some of those clay particles get picked up with that water, washed down, and deposited in the B horizon. So over time, the B horizon actually gets thicker and thicker as the clay particles get deposited deeper and deeper. How do you know you're in the B? Oftentimes you can look for color. If you see the sort of the most intense oranges, yellows, and reds in your soil, chances are you're in the B horizon. If the soil feels sticky and dense and moist in many cases, because certainly clay holds a lot of water, chances are you're in your B horizon. We get down to the C horizon. This is sort of a border layer between the well-developed A, E, and B horizons above, and the unweathered parent material, or in most cases, bedrock down below. So usually when you get into the C horizon, you see the clay content drop. The soil starts getting sandier, oftentimes more gravelly, and oftentimes it feels drier and looser because it doesn't have that clay there, causing it to feel thick and causing things to adhere together. Oftentimes the transition from the B to the C can be very gradual, so it's hard sometimes to figure out exactly where you are. But basically, if you see that clay content dropping and the soil getting drier, looser, and grittier, it's a good chance you're moving from the B to the C. And some of you may not dig deep enough in your soil to ever get down to the C, because sometimes these C layers are 4 or 4.5 feet below the surface. And then lastly, there's bedrock. So no matter where you are, eventually, if you dig down deep enough, you will hit solid bedrock. But that depth can vary a lot. In Prince William County, it can be anywhere from 20, 25, 30 feet up to 2 to 4 feet. If you live in the eastern parts of Prince William County, chances are you're in an area called the Triassic Basin, and most of the bedrock there is actually pretty shallow, 2 to 5 feet in depth. If you live towards the western parts, that's where you get into some deeper soil areas and you have to dig down a little bit more to get that bedrock. If you're to move even further east, if you go to a place like Old Town Alexandria, you might have to dig down 300 feet before you hit bedrock. So the depth to the R horizon varies dramatically, even over small areas of geography. But that's not really what we're concentrating on too much, not so much the big geological formations and things like that, even though I find those interesting. We're really looking to see what is this kind of combo system between healthy soil and healthy plants. How can we get healthy soil, which will then create the healthy plants that we're looking to have out on our surface that we can see when we look out our windows? Well, you really want an A horizon with lots and lots of organic matter in a nice, loose, what we call granular structure. Granules basically look like grape nut cereal. And worms are very important in creating that granular structure because a lot of that structure that we see, those little PEDs that we see up at the surface are actually worm casts, or for lack of a better term, worm poop. And it's these guys that give it to us. It's the living stuff within the soil that helps create this healthy soil plant system. But really, when we have a lot of organic matter going into the soil, what we're doing is feeding these critters that live in the soil. So remember, we add organic matter to the soil, and the microbes within the soil break down that organic matter during that decomposition process. They're not doing it for the good of the soil. They're doing it for themselves. That's their food. They're trying to grow and reproduce. But luckily for us, they're messy eaters, and they happen to release a lot of nutrients. They're sort of like leaving crumbs out in the soil. So they take in nutrients and organic matter for themselves, but they release nutrients out into the soil, which can then get dissolved in the water. And those dissolved nutrients are what's available to the plants. There's your granular structure. Nice, loose. Again, I kind of use grape nuts as sort of a term to describe what it looks like, because it's about the right size and shape. And this granular structure is usually very loose and light. There's lots of pore spaces, macropores between each of these granules, which allows air and water to quickly pass from the surface down into the soil and down to where the roots can access them, and where the microbes can access them too, because most of the microbes living in soil, they want a moist environment and they want an oxygen-filled environment as well. As that water passes through, the water dissolves the nutrients that were liberated by those microbes as they were breaking down organic matter, and that allows for the nutrients to be taken up by the roots. So it's a little confusing. We think of roots, working their way through the soil. Roots do not take up soil. In fact, they don't take up anything solid from soil. All they take up, two things: oxygen and water. So if it's taking up nutrients, which it has to do, those nutrients have to be dissolved in the water that it's taking. So you need to break down the organic matter, thanks to the microbes, to get those nutrients into a form that can be dissolved. And then you need water to get into the soil to actually dissolve the nutrients. And then when the plant takes up the water, it's taking up all those dissolved nutrients with it. And of course, it's a sort of a vice versa system. It's a virtuous cycle. Well-fed plants add a lot of organic matter back to the soil, and this powers the cycle. So healthy soil helps get well-fed plants. Well-fed plants adds organic matter, which creates this healthy soil food web, which creates healthy soil, which of course adds back to the plants. So they're both giving and taking. Now, we live in an urban area, and what happens in urban areas is a lot of human development. And unfortunately, development causes many changes in the soils, and basically all of them are bad. One big one is compaction. If we have this nice, loose, well-structured, granular soil, and we run over it with a backhoe, we run over it with a bulldozer, what happens? It becomes much more dense. A lot of those soil structural PEDs get completely pulverized, and the rest of the soil just gets packed back down. So it may look like soil after we're done, but it's soil that has changed significantly and is generally much, much more dense. So a compacted soil, we start off with this nice healthy soil, 25% by volume air, 25% by volume water, 50% solid. We run it over with development equipment. What happens? Well, it squishes out those macropore spaces, which allow the air and water to get in the soil in the first place. And we have a soil that is significantly more solid and thus significantly more dense. We lose a lot of those good natural pores or channels that allow air and water to get in. So loss of pore space. And this, of course, reduces the infiltration of air and water. Now we have that compacted, almost plate-like soil. Water falls on it, and a lot of it just doesn't have the ability to get down into the soil fast enough, so it becomes surface runoff. So I call this impervious light. Compacted soil generally is not fully impervious. It can still take in some water, but it's almost like it's halfway to an impervious surface, like a concrete, an asphalt, a rooftop, because it's not taking in nearly the volume that it could before. The other issue with compaction is it creates, again, this very dense but very strong soil, basically a soil that can be so dense and strong and hard that sometimes it can be difficult for roots to actually penetrate. So this is sort of a typical subdivision, new subdivision, suburban scene. We've got the new houses built, the road put down, and the developer comes in and puts these street trees there. Well, if you come back in 30 or 40 years, that tree ideally should be pretty much full grown, but in a lot of cases, you come back decades later and the tree really hasn't grown that much. And I think one of the reasons is with this compacted soil, especially in this, I think they call that the suicide zone, the grass there, the little strip of grass between the sidewalk and the roadway. The soil is so dense, it's difficult for those roots to penetrate out in the soil. And if the roots remain stunted, meaning unable to really penetrate beyond their initial root ball, the tree is going to be stunted as well too. The tree can only grow to the size that its roots will allow.
Dan, you have
And
5
here's a good
minutes.
example. Okay, here's a good example. This is along Pennsylvania Avenue between the Capitol and the White House. You can see the oak trees over on the left side here are very stunted compared to the ones on the right. And that's because they just don't have access to good soil. They're stuck between the compacted soil under the roadway and the compacted soil under the sidewalk, whereas the plants to the right have much more room. I'm going to kind of blast through these because I'm running late, but as soil is developed, it mixes all the soil layers, and this tends to disperse the A horizon throughout the rest of the soil. And if you don't have that concentrated band of organic humus and microbes up at the top, it really does stunt the nutrient cycling of your soils. So what is soil really? Is it the intersection of the hydrosphere, the lithosphere, and the atmosphere? Is it a mix of sand, silt, and clay, and organic matter? Yes, it is, but that's really describing the physical characteristics of the soil. When we think about its function, what it's really doing is it's providing a rich and diverse ecosystem that is a complex food web that recycles materials, especially nutrients. So really, I think combining all these three, it's kind of like the stomach, the digestive tract of the world. It takes in waste product like falling leaves and turns them into useful energy and nutrients that the plants can then take up. So how do you keep this soil stomach happy? You feed it, you give it good food. What does it eat? Not fertilizer. Fertilizer is like a vitamin. It provides nitrogen, phosphorus, potassium, and that can be very important, but it does not provide food, really. Some are organic and provide a little bit of food, but not really. What you need to do is add organic matter. Organic matter is what actually feeds the soil. You need that organic carbon. We eat vitamins in the morning. It's not going to fill you up. You also need your bacon, your eggs, your cereal, whatever you have. And within that cereal, that breakfast is actually the organic carbon. That's what gives us energy throughout the day. Same thing happens with the soil microbes. They need that organic carbon. What are some examples? Well, compost. You can buy it, you can make it yourself. And you can add stuff that's sort of like a cross between fertilizer and compost. This would be things like blended or composted manure or Milorganite, which if you're not familiar is actually Milwaukee treated sewage sludge, but it's been sold as a lawn amendment for over 100 years now, and it adds both nutrients and a lot of organic matter. Of course, you can do it much more simpler. You can just mow in your leaves in the fall rather than raking them up and taking them away, which of course is a lot of work. Leaves are a great and free source of organic matter that could easily be put back into your soil. You can recycle your grass blades instead of bagging them, just leave them on the soil, let them decompose. You can go a little bit heavier. If let's say you have a really compacted soil that's just not performing well, you can top dress it, basically rake out a thin layer of compost, thin enough that it's not going to bury the grass, and just rake it, an even layer over the entire soil. And within a matter of weeks, the earthworms will have incorporated that compost into the soil. This is a landscape company has laid these piles out before they raked it out. So it doesn't look like this after it's been accurately applied as a top dressing. And the simplest way to feed it, plant. You'd be surprised how much organic matter in soil is actually pushed out, exuded by the plant roots themselves. Plants have an interest in putting organic matter down into the soil because this feeds the microbes, and the microbes are the ones that decompose organic matter within the soil and thus return nutrients to the plants. So as a way to get the nutrients they need, the plants actually feed the microbes by pushing organic matter out through their roots and giving them a food source. So the more living plants that you have on the surface, the more living roots you'll have under the surface, and the more organic matter they'll be pushing out. So that really is the simplest way to feed the soil. And the other thing is, with your plants, what you want to do is keep the plant residues on site. So again, when the leaves fall, when stalks die, don't rake them up and take them off site and put them on the curb for the county to come collect. Try and incorporate them or just leave them on the soil surface so that they'll decompose and add their organic carbon back into the soil. When you're doing this, you're providing the soil with that organic matter, which is the base of the soil food web. That's going to make your fungi and your bacteria real happy. And our decomposers, our fungi, bacteria, are the ones that really power the nutrient cycle within soil. They're the ones that are decomposing all the organic matter that comes in and turning it into a form that can where the nutrients can then be released and taken up by the plant roots. A well-fed soil is a resilient soil. Give those decomposers, those bacteria and fungi, good food and let them do the work for you. It'll make your management so much simpler if you have that healthy soil, because the healthy soil does the nutrient cycling for you that you want to have in place to have healthy plants. And that is it. I've got my contact information there. So I know we're going to have a Q&A session now, but if a question arises a little bit later, feel free to send me an email or give me a call, and I'll do my best to answer it as well too. But for now, we can go over any Q&A that might have come in.
That's great. Thank you so much, Dan. And so we'll spend the next 10 minutes or so on Q&A, and then the breakout session will close for lunch at 12:30. So let's get to some of the questions. We'll start with Jerry's question. Having just delighted in reading Finding the Mother Tree, how well understood are the mycorrhizal communities in our region? How can lay people ensure their health?
I would say, I can't say I have any particular expertise in the types of microbes or the intricate relations that they have, but I also don't think you really need it. So a healthy soil will generally have the microbes that are needed. Basically, if you're looking out your window and your trees seem to be growing decently, that's a very good sign that you've got a healthy microbial ecosystem down below. It might be able to make it a little bit healthier, but generally, unless you are, dealing with, let's say you rip up a blacktop or something, or a basketball court, and you're dealing with the soil underneath there, that could be potentially just dead soil because it's been stuck under that impervious surface and so highly compacted. But if you've got stuff growing on your soil and it's growing fairly decently, that is almost a sure sign that you've got at least a semi-functioning soil food web down below. So I don't think you have to necessarily add inoculants or worry about, you can go buy mycorrhizae spores at nurseries around here. You probably don't have to do anything like that. Really what you want to do is just keep providing good organic matter and large volumes of organic matter to your soil, because the soil ecosystem is so complex and diverse that I don't think there's any really one thing you can do to boost one type of microbe over another. What you really just want to do is add organic matter that is the base of the entire microbial soil food web, and that's about the best you can do to keep them happy and healthy and functioning and cycling your nutrients. So I guess my advice is, don't worry too much about the specifics, just add organic matter and nature knows how to take care of the rest.
Great. And so just kind of reiterating a point that you made earlier. So the advice that says to add sand to clay soil isn't good?
It can be a little confusing because I'm assuming you are kind of coming at this as more of a general landscaper. I would definitely not spread sand over my entire property. Sometimes if you're doing some really intense growing in certain areas, like if you have a food garden in a small portion of your yard, perhaps adding some sand to that would be worthwhile. But generally speaking, I would still push you to go add organic matter first, because adding sand potentially can loosen up a clay soil, but adding organic matter can also loosen up a clay soil. And as you're adding that organic matter, of course, you get all those auxiliary benefits like feeding the soil microbes and adding more nutrients to the soil, where sand is basically an inert material. It can change the soil texture in a very small area, but that's all it can do. It's not going to add any food for the microbes. It's not going to add any nutrients to your soil. So I'd say get multiple bangs for the buck by adding organic matter rather than adding sand.
So we have a couple of questions about, planting and treatments with the soil. So when you're doing a planting, what kind of soil remediation perhaps you would do during the planting, and how compact should you be packing the soil around seeding or seedlings?
Well, the good news is being a native plant symposium like we're in today, you don't really need to do much of any soil remediation within the planting hole for a native seedling, because our native seedlings, our native species of all types, are accustomed to the soil that we had. So, again, we get a lot of complaints about red Virginia clay. Well, if you look out in our forest, they're, got these huge 150-foot tall oaks and everything else. Those plants are doing just fine in our red Virginia clay. So I would say if you're planting natives, maybe you want to put in a little compost, but generally I just say plant it right in the soil you have, unless you know that the soil you have is in really bad shape. Again, if there's a spot in your yard where nothing will grow and it feels just very, very compact and very dense and water puddles there, then yes, adding in some compost at the time might be a good idea. But for the most, unless you have that really, really bad soil, for the natives, I say just plant them because they're accustomed to our growing conditions. And what they'll do is as their roots start spreading, they will start adding the organic matter to your soil. And as the leaves start falling, they'll add the organic matter as well too. So kind of take a light touch and let nature do most of that work for you, unless you have that really, really bad soil to begin with. In terms of the compactness, you do want to have a good root to soil connection. So I usually say, pack it down pretty hard, not with your feet, but with your hands, and make sure you've compacted the soil around your seedling fairly dense with your hands, and then water it, because watering will allow the disturbed soil within the soil hole that you just dug to sort of collapse back down and make a good connection with your new roots.
Great. Building on that, there's a couple of questions in terms of, that bad soil, that urban soil that we have. Perhaps you have like some infill from construction work or a lot of gravel. What recommendations would you have if that is the situation to start repairing the soil?
Well, again, there's sort of two ways, and it can be hard to say from the outset. But if you've got really, really bad soil and you're looking to do a complete change of your landscaping, and this is more of a problem in newer development where the lawns tend to get more compact. You could potentially go whole hog and put a top dressing of compost on your soil and then till it in. Deep till it for 6 to 12 inches or so. But of course, that's going to rip up whatever you've got there. That's going to rip up your entire lawn. If you've got trees there, it's going to disturb the tree roots. So that's kind of if you're starting from scratch, from a really bad position. If you're starting from a position where the soil may not be great, but there are things growing on there, maybe you want to do that compost top dressing where you spread it out over the surface in a very thin 1/4 to a 1/2 inch layer or so, and let the natural worms and what have you incorporate that on their own. And over time, that's going to build up the soil organic matter and start recreating that natural A horizon. And then you want to plant in it. You want to make sure that you get good, deep-rooted native vegetation into that soil. So as those plant roots start to penetrate down deeper into the soil, they are loosening it up just by dint of pushing their roots through the soil, but they're also adding organic matter deeper into the soil and allowing the soil to loosen on its own slowly, but it will eventually start loosening. And if you got decent soil to begin with, again, you probably don't have to even do the compost top dressing. You just plant a lot of plants and keep as much of the residue on the soil as possible so that you get that natural organic recycling. The plants grow, they spread their roots out underground, they grow leaves above ground, you leave the leaves in place, you mow them in place, you let them decompose in place, and the natural cycle takes over after a few growing seasons.
Great. We have a question regarding the cicadas and if they had any impact on the soil when they emerged last year.
I don't have a resource I could point to or an article I could point to say yes, but my inkling is that they do, because in effect, they are great burrowers, and every time they pop up, they've created a new, pretty large pore space that oxygen or water could use to pass down into the soil. So I can't see them as a negative. Yeah, they're basically billions and billions of pores that they created as they emerged from underground and popped up to the surface. So I think that's a good way to loosen up the soil and increase the infiltration rate.
Then going back to some of our burrs, some folks have mentioned that the earthworm is non-native. Most of the earthworm species that we have are non-native. And so what did the soils look like in North America before earthworms arrived?
It basically, it was kind of controlled by where the glaciers were. So again, I can't say I'm an expert in this, but my understanding is that those areas that were heavily glaciated, basically the glaciers came and just stripped everything off. You imagine there's a 2-mile thick wall of ice creeping over the surface. Everything's just going to get pushed off. So those areas north of us, from New York City up into the Midwest and into New England, were basically the glaciated areas. And those areas, the soil was basically stripped. And as the glaciers melted, new soil was eventually created, but it was mostly earthworm free. Down by us, obviously we were affected by the glaciers. Our environment would have been a lot different, but the glaciers were not here. They stayed to the north of us. So my understanding is we always did have earthworms, not necessarily the species we have. Certainly your night crawlers and other things are imported, but they don't seem to be causing real problems around here because we have soils that have developed with worms in them because we were never stripped off by the glaciers. Where you are seeing problems are sort of the upper Midwest, Wisconsin, Illinois, things like that, where they have a really thick forest duff layer naturally in their forest soils because there were not those earthworms burrowing through and incorporating that material deeper down into the soil. And they have species that grow up there, both trees and soil species that are sort of grew and accustomed to having that really thick duff layer. But for us, I would say earthworms are generally a really good thing down here. So if you're gardening in northern Wisconsin, they could be a problem. Here, I really wouldn't worry about it. I think even I will call them invasive. I would say they're introduced species here, but not necessarily invasive because they're not really harming us. Now, there are some ones we have to keep an eye out. There's some new earthworms coming from Korea and Japan that really do cause some problems. And unfortunately, we do see them around here in some spots, but they don't seem to be widespread just yet. So your standard burrowing earthworms, even your night crawlers and things like that are going to do good stuff for our local soils.
Great. So we have a couple of minutes to go over a couple more questions. Would you be up for that, Dan, or do you need to head out? I know we're at time, so just want to check in with you.
No, I can stick around. I'll stick around.
Okay, great. So let's see. I had one here. Oh, getting into more of the technicals of soil. Could you explain the term base cations? I'm interested in how a moderately acidic soil containing base cations can support more base-loving plants.
Okay, so base cations are basically calcium, magnesium, and potassium. So these are the nutrients. Cation is just a general term for a positively charged molecule. And the ones that we find in commonly in the soil are calcium, magnesium, potassium. There's others, but those are the big three. Generally, the more basic the soil is, meaning the higher the pH, the more of those nutrients you will find. I wouldn't worry so much about the levels of those nutrients. When you send out for a soils test at Virginia Tech, they'll send back information about how many of those nutrients are in there. I'd rather what you really want to look at is the soil pH. And if you're trying to grow native soils, every plant has its own unique pH that it likes, but generally if you're in the pH 5.5 to 6.5, 6.8 range, somewhere within that range, which most of our local soils are, you're in pretty good shape. Our native plants are kind of accustomed to grow into that slightly acid to somewhat acid type of environment. Now there's exceptions, if you're trying to grow wild blueberries or mountain laurel, those are acid-loving plants. Hydrangeas and azaleas are acid-loving plants. They're going to want more like a 4.5 to 5.5 range. So I'd say there's, if you're trying to find new plants to grow, what you might want to do, well, actually, definitely want to do is get the soils test first, see what the pH is. And rather than bothering too much with trying to change the pH, I think it's easier just to plant to the pH that you have. But in those rare instances where you do have a artificially high or low pH, or you do need to change it for whatever reason, it's not too hard to do with a little bit of lime to boost up the pH, or with a little bit of sulfur to take it down. So in an acid soil, you can still have lots and lots of calcium and magnesium. But again, what we see is soil pH is important because at a certain level of pH usually means that there's a certain level of nutrients that are available. Blueberries don't like high pH because they can't grow in basic soils. They don't like high pH because they don't like the level of nutrients that are available to them at that high pH. So it's not so much that you want to control the level of calcium or magnesium. If you control the pH, you're basically doing that by proxy. So I would say aim for that good sweet spot, 5.5 to 6.5, 6.8 pH. And as long as you're staying within there, I wouldn't worry too much about the specific levels of nutrients that are in your soil.